Corollary 2.4. If A is a Banach algebra with identity, then A, the closure of a proper left, right, or bilateral ideal is a proper left, right, or bilateral ideal. B, a maximal left, right, or bilateral ideal is closed. Proof. A, let M be a proper left ideal, and let G's of L be the set of left invertible elements in A. It follows that M intersect G's of L is empty. So that's let me explain why this intersection M intersect G's of L is empty. So ideal means that you take any element in GL, and you take any element in M, then the product is in M. Okay, so suppose this is not empty. Okay, so suppose M, that means M contains a left invertible element, let's say B, okay? B is left invertible and also is in M. We are going to get a contradiction, okay? Since B is left invertible, it has a left inverse A. So A times B is 1. So by the definition of a left ideal, this A times B is a member of M. So M contains identity element 1. If M contains identity 1, then it contains every element, because you take any other element times 1, that element should belong to M. So then M is equal to A. But M is supposed to be a proper left ideal. Proper means it's not equal to A. So this is a contradiction. So that's why M intersect G's of L is empty. So basically, we need to understand the following, okay? Any proper ideal does not contain an invertible element. The left ideal does not contain any left invertible element. The right ideal, proper right ideal, does not contain any right invertible element. Any proper ideal does not contain any invertible element. So we should keep that in mind. Okay, so M is intersect G's of L is empty. So this says M is contained in A minus G's of L. But the G's of L is open. So M is contained in this. A minus G's of L is closed. So M is contained in this, okay? So G sub L is open, so A minus G sub L is closed. So since M is included in this closed set, so then the closure of M also is contained in this closed set. But by the definition of ideal, we can verify that since M is a left ideal, the closure of M is also a left ideal. Since the closure of this is included in A minus GL, so closure M is not the whole space A. So closure M is again a proper left ideal. Okay, it is a proper left ideal. So this has proved that the closure of a proper left ideal is a proper left ideal. The same reason, same argument works for right or bilateral ideal. In other words, the same argument shows the closure of a proper right ideal is again a proper right ideal. The closure of an ideal, proper ideal is again a proper ideal. B, the maximum left, right, or bilateral ideal is closed. Okay. The maximum left, right, or bilateral ideal is closed. So B, okay. If M is a maximal left ideal, then closure of M is a proper left ideal by A. Hence, closure M is equal to M by maximality. Yeah, you see, M is already a maximal left ideal. But the closure of M is again a proper ideal, which contains M. So M, since M is maximal, they must be equal. So closure M must be equal to M. So M must be closed. So we have proved that a maximal left ideal is closed. Same argument shows a maximal right ideal is closed. A maximal bilateral ideal is closed. So proposition 2.4 has been proved. Then if A is a Banach algebra with identity, then every proper left, right, or bilateral ideal is contained in the maximal ideal of the same type. For this, we need to prove this, we need to use Zorn's lemma. Okay. So the argument, we are not going to go into details, but the argument goes this way. So you have a maximal, you have a left, suppose we have a left ideal, okay? We have a left ideal. Then if it is not maximal, we have a larger one. Then if it is not maximal, we have a larger one. Then we get a chain. We get a chain of this. We get a chain. Then the union of this, chain Of course, it is an ideal, but we can see it is a proper ideal because any one of this does not intersect G sub L. So the union does not intersect G sub L. The union does not contain any left invertible element. So the union is proper left ideal. So this shows that any chain has an upper bound by Zorn's lemma. It contains a maximal element. So that's why there exists a maximal left ideal. So the proof of this depends on Zorn's lemma. Zorn's lemma is a kind of equivalent to axiom of choice. Okay, that's kind of deep stuff in mathematical logic. Theorem 2.6. If M is a proper closed ideal in the Banach algebra A, then A minus M is a Banach algebra. If A has an identity, so does A over M. Proof, okay. We have already seen that A over M is a Banach space. Yeah, because M is a proper closed ideal, so it is a proper closed subspace. So by earlier knowledge in this course, we see that A over M is a Banach space. Okay, since M is a closed subspace, so we can divide to get a Banach space. So then we are going to see that the product is well defined. So the element of A over M is like X plus 1M. Okay. Suppose we have another one with Y plus M. So we want to multiply. We multiply, we get X times Y plus X times M plus M times Y and plus M times M. We just break the parentheses, okay, as if these were numbers, okay. So then we can see that in this formal calculation, we can see that in order for this product to be well defined, we need this Xm is contained in M. So that's why M has to, in order for this to be a Banach algebra, in order for the product to be well defined, X times M must be in M. So M must be a left ideal. Then My has to be in M. So M has to be a right ideal. So M has to be a bilateral ideal. So that's why it is not enough to require M is a subspace. It is not even enough to be a subalgebra. It must be an ideal. So we need to review the definition. Okay, what is the difference between a subalgebra and the ideal? Given that this M is a subspace, okay, in order for it to be a subalgebra, we must, it requires that X, Y belongs to M if X and Y belong to M. We say it is an ideal. This means X, Y belongs to M. If X belongs to A and Y belongs to M, then X, Y must belong to M. So we allow X be in A So that is the difference between an ideal and subalgebra. In order for this product to be well defined, in order for A over M is a Banach's algebra, we must require M to be an ideal, a closed ideal. So now we can see that if it is a closed ideal, then this element times this is a well-defined product here, xy plus m. So the multiplication on this is well-defined. And the remainder, the axioms are satisfied, and the remainder of the proof is left to the student.